some of this, if you remember. My block of metal. If I got a force going this way, page 1. If I got a force going this way, alright, this metal bar is going to extend a little bit. So it's going to go, because that's in tension, because we're pulling apart. So it's going to move this way. And if we had length like we did last week, there's my length. That force will tend to make this thing move a little bit. We can call that delta L, or we can call it X to you. It's in tension, so it's pulling apart. It's pulling apart. So it's extending. And the other way we looked at was this. We looked at this. My metal bar again. And if I put a force this way, it's going to shrink the metal bar. It's going to shrink, it's going to squash it that way. So that was my change in length, or my X. And this one is compression, which is squash. So that could be the length there. Okay, that was last week, or this, yeah, last week now. All right, so things get pulled and things get, this is mechanical principles. I've changed now the name of it because it's the proper name. It's mechanical principles, yeah, unit 8 I think it is. Not hair and beauty. I just want to do hair and beauty. Should you do hair and beauty for an hour and a half? Obviously less of the hair, more of the beauty perhaps, for me anyway. So obviously we also looked at, well not obviously, but you know, if our metal bar has got an area, which it will, right, so we could have a round bar like this. Oh, this is, it's still statics. This is just stress and strain now. If you want to write it down, because oh you weren't here last week. You stress and strain. This is Daniel Greenshield. Did you get my email from last week? Because I this stuff on Moodle. There's loads of videos on Moodle now, right, under stress. So if my metal bar's got this, the force pulling this way or squashing it is going to induce a stress. And last week we did it. Stress is force over what? Do you remember? Force over area. Force over area. In this case here, in this case, it's the area of the circle. Don't forget, this has got to be in newtons and this has got to be in meters squared. So the area of a circle, you can either use pi r squared or you could use pi d squared over 4. It's up to you. Obviously, if I give you a diameter, say it's 10 mil. If I give you a diameter which is 10 mil, you've got to convert it into meters first, though, right? So you need to divide it by 1,000. Because there's 1,000 millimeters equals 1 meter. The benefit of using pi d squared over 4 is what? Anybody tell me? Can you remember? What could go wrong if you use pi r squared? Because I think a few of you made the mistake last week. What could go wrong if you use pi r squared? What could go wrong? There we are. You can use pi r squared, all right? But don't forget, if I give you diameter, which I always will give you diameter, you need to halve it. Because the radius of that would be 5. It's one less mistake to make. If you use pi d squared over 4, you haven't got to bother halving because you've already got the 10. All you've got to worry about then is making sure it's in meters. That's why we divide by 1,000. Okay, so that was last week. And obviously we might even have this, because you either get a round one or a square one. If we get a square bar like that, let's do a bit of perspective perhaps. That's my square bar. The area we're going to use is this area here. So this could be width, and this could be height, say. So it's the area of the square, or the rectangle in this case, isn't it? It's this area here. Width times by the height. 5 mil by 10 mil, something like that. You just need to make sure the area is in meters squared, and the force is in newtons. Newtons. Right? That was stress. There's the formula. Force over area. It's the same for shear compressive stress or tensile stress. Same formula. Right? It's the same formula. Stress is force over area. Obviously, one's going one way and one's going the other. Now we can also work out the change in length, because we also looked at a thing called strain. So a force will give you a stress, and a stress will give you a strain. You're straining, like when you're lifting weight or something, you do strain, right? So strain really, right, is a measure of change in length, measure of change in length, change in length, which we can call delta L or X. This thing here, this thing, or this thing. Right, for now, it doesn't make no difference if it's squashing it or pulling it apart, right? It's the same thing. Next year we talk about, because one's going one way, one's going the other, so one's a positive and one's negative, but for now we'll just keep it the same. So strain, if anybody can remember, the formula for strain was change in length over original length. Another formula you could write down. No units. So length over length. Okay. So it's the change whether that's been squashed or pulled apart, change over really the original. That's all that is. So the strain is the change over the original. If that's in millimeters, this has got to be in millimeters. If that's in meters, that's got to be in meters. So it doesn't matter what unit they're in, as long as they're both in the same unit. It's a length over length. It's a ratio, really. Huh? That was strain. What page was this? Page 3. Page 1, page 1. Page 2, page 3. Page 3. And then page 4, we did a thing called elastic modulus. Elastic modulus. Modulus, which is also called Young's modulus. Young's modulus. Symbol is E. It's how stretchy something is, how elastic something is. Going back to materials, it's this. If you pull something apart, like we've sort of talked about, it does a straight line and then does something like that. This bit here, the straight line bit, is where it obeys Young's modulus. So something that's quite rigid, okay, for example, diamond has a high Young's modulus, because you need a lot of force to make it stretch, right? Whereas plastics, it goes like that. So the lower the Young's modulus, so low Young's modulus, just means high elastic. So diamond has got a high Young's modulus. Steel has got a high Young's modulus compared to plastic. So you should get bigger numbers, right? So if you don't know what the material is, but you're getting a low Young's modulus, the material could be a plastic material. The formula for that was, can anybody remember? The formula for Young's modulus was, E is a symbol. Anybody know? Anybody remember? Well, we've worked out strain and we've worked out stress. So there's the clue. Stress over strain. Right. So this is number one formula here. That's number one. Number two. Number three. And obviously you should know what area is anyway, right? Makes no difference if it's tension or compression. It's the same stuff. Same stuff. Alright. Is everybody alright? That was a bit from last week. A bit from last week. Type a dot if you're okay. Let's do a couple of examples then, just to back it up. Examples. Let's do some examples. Let's do some examples. Let's say we've got a metal wire. Metal wire of, I don't know, 1.5 mil diameter. Alright. It's got a force pulling on it, so the force pulling on this wire, so here's my wire, say. Alright, the force on it, so the force coming here, pulling it apart, is 1,200 newtons. The length of this is 2 meters. Metal wire 1.5 diameter, it's got 2 meters, 1,200, and that force, right, so the force, so the change in length, let's say it stretches it 0.2 millimeter, which means, you know, it's been stretched, exaggerated, right, 0.2. So the force is pulling this wire and is stretching it by 0.2 of a mil. We need to work out stress strain. So we need to find stress. We need to find strain. And we need to find Young's modulus. And we know stress is just force over area. Got the force, we can find the area. Strain is change in length over original length. We've got both of them. And Young's modulus was just stress over strain. No trick here. What I might do is I might just put it all up here. A bit more room then. Change in length equals 0.2. Force 1200. Bit more room. So first of all we need area. So it's a round bar, look. So area is going to be, I'll use pi d squared over 4. So area is going to be pi. Don't forget we need to be in meters, so we'll divide this by 1,000. Pi d squared all over 4. That, or you could use, or pi r squared, is up to you, as long as you make sure you get that correct. So diameter is 1.5, the area is, look, I'm just using this formula here, I'm just using pi d squared over 4, so I haven't got to bother dividing the diameter by 2. So 1.5 divided by 1,000 to get that into meters. We'll square that, times it by pi, and divide it by 4. Gives you a number. Press E and G on your calculator. Anybody tell me what it is? A bit of engagement, please. What's the answer? 1.5 divided by 1,000 squared times by pi divided by 4. Check it again, column. Just make sure I check. 1.5 divided by 1,000. 1.5 squared. Only square the diameter. Times by shift pi divided by 4. Well done, Benjamin. Yes. 1. We'll use 7.6, so 1.7, let's go to 7 then. 1.77, something like that, times 10 to the minus 6 meters squared. Make sure, column, you know what you did there. Right. It's the d squared, right? Because if you get the area wrong, everything else is going to be down the Swanee, because the area links to stress. Then stress links to strain, and then everything else. So if you get the area wrong, okay, to get the area correct, that's the area. You get the same answer if you do pi r squared. So then stress now is just force over area. We know the force is 1,200 and the area is 1.77 times 10 to the minus 6. Someone to give me that answer. It should be a really, really big number. Press E and G on your calculator like we did last week to get mega probably, and see what you get. All do it, so you know you're getting the right answer. You should get a big number. You should get a big number with 6s and 7s and 9s and 6. Press the E and G button, and it should then convert it to 10 to 6. Press the E and G button, and you should be getting. Anybody brave enough? Apart from Callum and Benjamin. It should not be minus 6, Callum. It should be power 6. I'm assuming it's a typo. It's always big stress. There we are. 6. Yeah, they are 677. So 677.9. So we'll leave it like that. Times 10 to the 6, which we could say perhaps is 6. Let's round that up. 678 megapascal. Because 10 to the 6 is mega. So if you pressed ENG on your calculator, it'll do that, rather than writing all them numbers down. That's the stress. Thank you very much. Next one, strain. Next one is strain. So we know that strain is change in length over original length. So it's 0.2 mil. So this is 0.2 of a millimeter, and the length of the thing is 2 meters. So length is 2 meters. Okay, now we've got millimeters and meters here, so we need to be in the same unit. Whatever you pick, right, you've got to be in the same unit. Right, so I'll pick millimeters. Right? It makes a difference. You should be meters all other times. But when you're doing strain, as long as you're in the same unit, as long as the top and the bottom is in the same unit, you get the same answer. And because it's so small, right, I'm going to stick to millimeters perhaps. So change in length is 0.2, so just use 0.2 because that's that in millimeters. And I've got 2 meters. How many millimeters are there in 2 meters? One with the other. You either divide or times by something. 2,000, because it's going to be 2 times 1,000. So it's going to be 2,000 millimeters. Work that out. Right, work that out. 0.2 divided by 2,000 joules. Press ENG. Press ENG, and it should give you something like this. Something like that. 2 divided by, see, it's tens, hundreds, isn't it? No units, no units. Make sure you get that. Now, just to show you, you could do it in meters now, right? So we could do it in meters now. So 0.2 millimeters is going to be 0.2 divided by 1,000. I'm going to do it now in meters just to show that you get the same answer. So 0.2 millimeters is divided by 1,000 to get it into meters. And now the change in length is 0.2 divided by 1,000, and original length is going to be length, which is going to be 2 because now we're in meters. And we should still get the same answer as this. 0.2 divided by 1,000, all right, to convert it into meters, and divide that by 2 then. Press ENG, and you'll get the same answer. So it doesn't matter really what you do, as long as you're in the same units. As long as that and that are the same units. You can be in miles, you can be in kilometers, you can be in what you want. You get the same answer. That's my strain. Is everybody okay with strain? Type a dot if you're okay with strain. Right, as long as you're in the same unit, you should be alright. Okay. Is Aaron back yet? Is Tio here with us? No. So that's the strain. Now we need to find Young's modulus. That's going to be stress over strain. Well, there's my stress there, look. Don't forget the mega. That's my stress. And my strain is here. That. So I'll do it in this little box. So Young's modulus, E, how stretchy it is, say, is stress divided by strain. We know the stress is 678 megapascals. Right? We'll use that because it's rounded up, but we'll still use it. 678. Don't forget the mega. Don't forget the megabit. Don't forget the megabit. Don't forget the megabit. All right. All divided by the strain, which is that there. 100 times 10 to the minus 6. It's going to be a big number. It's going to be a big number because it's a very big number divided by a small number. Press ENG at the end, and then somebody give me an answer. Somebody write the answer in there. Do it tidy though, because this is going to be saved. Don't make a mess of it. Just somebody do it. Do it down here, but don't scribble all over this, because I'm going to save this. So if you make a mess of it, you're making a mess of yourself. 678 to the 6 divided by 100 to the minus 6. Press E and G, please. Well done. Because your calculator. Press E and G to get it into. Right, it's a funny number, isn't it? So 678 to the 6. What's that? I got 679. Okay. 678 times 10 to the 6 equals that. Divided by all of that, which is 100 to the minus 6. Press equals. Now your calculator may give you this. Your calculator may give you this. Because it might. Your calculator may give you this. 6.78 times 10 to the 12, right? Right, which you could say, because it's like 12 is tera. But if you press E and G, because normally Young's modulus is giga, right? If you press E and G, it should move it for you. So it's the same answer as this, 6780 times 10 to the 9. Just have a check there, where we wrote that. They're both the same answer, and they're both the same answer. You should be getting that. Just check. Dan, just check again. Just check me, Dan, make sure I'm correct. 679. 10 to the 6 would be 6, 7, loads of them. So obviously, this now is 6780. 10 to the 9 is that. Or that could be tera, but we'll keep it in giga. Stress over strain, it's a very big number divided by a very, very small number. Because we haven't got a lot, we've only got 0.2 millimeters, right? It's very, very small change, look, very small. Minuscule, actually. That's why we've got a very, 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 very big number. Stress over strain, is everybody alright? Everybody get them answers? Now, you'd probably get 678, but if you've got something wrong with the area, or you haven't put K in, or something like that, you haven't put 1,000 in, or you might be a bit bigger, a bit smaller. Stress over strain. Everybody right? Let's do another one then. Let's do another one. Give you a square bar. Here's my square bar, or rectangular bar, whatever you want to call it. Let's just say it's got a force going this way, squashing it. Let's say that's 20. It's the same stuff, right? In compression, it makes no difference for us anyway. It's going a different direction, but for now we'll just keep it. So it's going that way. I'll give you a length. Let's just say it's 500 mil. Long, right? I'm going to give you, whatever this material is, I'm going to give you this, Young's modulus. Young's modulus. E equals 85 gigapascals. So I've given you that. Whatever this material is, that's the Young's modulus of it. Don't forget giga is 9, so we'll just do that. I need to give you some lengths, so looking straight on, right? So this is my square bar. Here's my square bar like that. So this could be 30 mil, and this could be 10 millimeters. So it's 30 there, look, and 10 there. Head on, that's all right. So it's a rectangle, so we need to find the area of that rectangle. So we've got to find, or you've got to find, or we've got to find, let's find the stress. We need to find the stress. We've got to find the strain. Same formula, just slightly different this one, right? Stress, strain, and we'll also find, number 3, the amount bar compresses. Because it's been squashed, so it's going to go that way, innit? Amount the bars compressed. So that is just change in length. Don't let that confuse you. The first thing we need to find is stress, so we need to find the area, because stress is force over area. Here's my area. So area is just the area of this. So area is the area of this square. And this rectangle really, innit? Is that? So it's 30 times by 10. But you've got to divide it by 1,000. Right? You can't just do 300 divided by something, but so 30 millimeters, so divided by 1,000 to get into meters. See what you get. You might get something like this. Right? Because there's a quick way of doing it. You can just times them together and divide by 1,000,000. But 30 divided by 1,000, just so we know, 30 divided by 1,000 times by 10 divided by 1,000. Press E and G. Okay. And all I've done there is I've multiplied 30 times by 10 to give me 300, and then you've got to divide that by 1,000,000. Right? So you can just put the -6 on the end of it. That's the quick way of doing it. But always go step by step, just so you don't forget things. So now stress is force over area. We know the force, it's 20 kilo. Don't forget the kilo. 20 times 10 to the 3. All divided by the area, which is 300 times 10 to the -6. Alright. Gosh, what stress is in the command. So, force over area, somebody do it please. Give me an answer. Who's brave enough? Somebody who hasn't typed for a bit. It should be a big number. Oh, depends if you're, yes, you never know. Ooh, devil. You're correct, Sam. Well done, Sam. It's 66.67. Don't like sixes, really. No, it shouldn't be gig, it should be mega. It should be times 10 to the 6. Let me check again. 20,000 divided by that area, which is 300 to the -6. See if 6. Press ENG 6. You should get 10 to the 6, Sam. Does everybody else get the same as me? So we were all correct together. 66.67 mega pascalios. I am right, yeah. Am I right? Yeah. It's mega, isn't it? Yes, it is mega. I'm losing my mind, am I? 6, yeah. Always check, see, always check. That's the stress. That's the stress. And that's the stress, that's the stress. Are we all... Oh, that's the stress. Alright. Now then, number 2, we've got to do strain. Number 2, we've got to work the strain out. Now, last time we did strain equals change in length over original length. Right? Now, do we know the change in length in this question? Do we know it? No, we don't. Oh dear, dear, dear. We've got to find it in the end, look, but we don't know the change in length. So we can't use that formula. Oh no, let's go to Vevwig and have an ice cream, right? So we can't use that. So we need to find another formula. Well done, Daniel. We need to find another formula with strain in it. Well, hell's bells. Here we are. Here it is, look. E is stress over strain. So we know E and we know stress. Because look, there's E. I've given you E. And we know stress. All right? So we can use this formula here. E is stress over strain. So Young's modulus is stress. Now you'd have to rearrange it though. Stress over strain, right? It's worth writing this down if you're struggling with rearranging. So first of all, I need to find strain. So I'm going to make things easy. I'm going to bring the strain up. It's divided by there, so I'm going to multiply both sides by strain to bring it across like that. I've multiplied strain over here, so it cancels out. And then I'm going to leave the strain here, and I'm going to move the E down, because E is times by. I'm going to divide it both sides. So do the same thing to both sides. It gets rid of it on the left, and we have it there. That's the formula. Strain is stress divided by E. Don't forget strain is going to be small, right? So stress, so we know what stress is. It's 66.67. So so we can divide one by the other. So we know that stress 66.67. Don't forget the mega, and E is 85 giga. 85 giga. Right? Get a smaller pen. And we know that strain is stress over E. So stress is 66.67 times 10 to the 6, all divided by E, which is 85 times 10 to the 9. Don't forget strain should be a small number for us because we don't expect a lot of change in lengths. So 66.67 power 6, divide that by 85 to the 9. Press E and G because you might get 10 to the minus 4. Press E and G. E is Young's modulus, Joe Curtis. It's Young's modulus. It's just how stretchy something is. So the symbol for it is E. So something with a high Young's modulus means it's quite rigid, or quite, like, you know, cast iron has got a high Young's modulus because it's not very stretchy. But plastic will have a low Young's modulus because it's very stretchy. That's what it means, right? But it's elastic modulus. For example, this question here, look, the one we did previously, look, 678 times 10 to the 9. That's a massive, that's very, very stiff material because it's a big number. That's all it is. It's how stretchy something is, right? So the bigger the number, the less stretchy it is. So if you put that in there, 66.67 to the power 6, divide that by 85 to the 9. Gives you a number. Press E and G, because I don't 10 to the minus 4. Press E and G, and it should do like Williams got. There we are. Alright, so you should get, now if you press E and G on your calculator, 784, we leave it at that, times 10 to the minus 6. No units. because your calculator may give you this. Your calculator may give you 7.84 times 10 to the minus 4. Nothing wrong with that answer. There's no symbol for 10 to the minus 4. There's no symbol. 10 to the 3 is killer. Micro, milli. This is micro. 10 to the minus 3 is milli. That's why they don't like use centimeters, because centimeters is 10 to the minus 2. It's centi, right? Anyway, but if you get that number, press ENG, and it should give you it in 10 to the minus 6. That's my strain. Thank you very much. Strain, quite small. So we've done that. Done that. We need to find how much now it squashes by. So it's just changing length. So this one's, page we on? Page 9. So we know that strain is change in length over original length. We need to find the change in length. We know the length because we do. It's 500 millimeters. So we keep it in millimeters. And we know the strain is, what's the strain? 784 times 10 to the minus 6. 784 times 10 to the minus 6. So we need to find delta L. We need to find this. We don't know what this is, but we'll rearrange the formula. I'm going to bring the L up. I'm going to times both sides by L. So now I get this. So strain times by L equals change in length. So the change in length, now whatever we multiply now, right? So strain is 784 times 10 to the minus 6. Multiply that by 500 millimeters. If you multiply this by 500 millimeters, you'll get the answer in millimeters. So you can do it that way if you want to. Or if you multiply it by a meter, you'll get the answer in a meter. So what's 500 millimeters in a meter? 500 millimeters is, what is it? It is 0.5 of a meter. So times that 784, whatever you've got in your calculator, look. So I'll just round that up then, because that is going to be that. So 784, that's the strain, times that by 0.5. Okay, I'll divide it by 2, whatever you want to do. So the answer is 392 times 10 to the minus 6. Very small, look. Very small. Meters. You could also, if you wanted to, because it might make a bit more sense, if I multiply that by millimeters, it comes out in millimeters. Because it's so small, right? So if I multiply that by 500 millimeters, it's going to come out in millimeters. Right? So you can do that if you wanted to. It just makes it a bit more, because I can picture what a millimeter looks like compared to what a meter looks like. That comes out 0.392 millimeters. It's the same answer. I can just picture 0.3 of a millimeter in my head better perhaps than all of that. So if you multiply it by millimeters, it comes out in millimeters. If you multiply it by a meter, it comes out in meters. 0.392, 0.4 of a millimeter is not much, is it? I can picture that in my head better than I can. But they're both correct. Da iawn. Everybody right? Everybody right? Everybody right? Everybody right? Everybody right? Everybody right? Now then, I'll just show you this. 8, 9, 10. If I write these words down, safety, oh, it keeps trying to do that, safety factor. What do you think safety factor means? Or factor of safety? Factor of. What does it mean? If something's got a, what would you rather be on, right? If this plane, here's my plane. If that's my plane there, right? Plane A. Lewis James Airlines, LJ Airlines, right? It's got a safety factor of, say, I don't know, 2. Or you've got a plane over here, right? Plane B, and it's Daniel Greenshields airline, takes off from Gubbert. Daniel Greenshields Airlines plane's got a safety factor, right, of 10. Which one is the safest? Bearing in mind, safety factor, the higher the safety factor, might be, because it's got a safety factor of 10. Right, so the bigger the safety factor, it's how much safe it is. Now, what would happen if for some reason that Daniel Greenshields, right, when he was designing this plane, went out in Cardigan and he made a couple of mistakes and he forgot to do something, so now his safety factor is 0.5. Would you go anywhere near DG Airlines? Would you? Or would you fly with LJ Airlines, who's got a safety factor of, well, obviously, yes. Now, LJ Airlines has got a safety factor of 2. DG Airlines has got a safety factor of 0.5. It's below 1, right? It's below 1. So if it's below 1, it's just about right. But 0.5, you're going to crash. That's what safety factor is all about, is how safe it is. It's linked to the material, the property of the material. So we'll be using how much force we need to break the material. So, close down, deaths. Right, all go for LJ. Now, safety factor of 2. Okay, it's quite good. Now, you can link it. Why is the safety factor? What's the safety factor on the motorway? Because you can link it like as in miles per hour wise. Safety factor. Because you could say the safety factor. What's the speed limit on a motorway? 70. 70 miles per hour is the safety factor, right? Because obviously cars can cope with going more than 70 these days, right? Cars can cope with going more than 70 these days. Right? So they may not do you, the police. If they catch you doing 70 on the motorway, they may not do you, right? If you're doing 110, will they stop you? Will the police stop you at 110? They can try, right? They might stop you at 110. Anything over 100, right? Really? Because on a motorway, all the barriers on a motorway, if you're going over a bridge, right? If you're going over a bridge, there's a very good picture, right? But here's the road. That's a barrier. Then you've got barriers down the middle as well, perhaps. And you've got barriers this side, right? All the Arco things, right? There's the things. Here's the cars going this way, the cars going that way, cars going that way. The barriers are meant to stop you what? The barriers are meant to stop you from going through. 70 mile an hour, they'll be alright. But 100 mile an hour, they can't guarantee it. Not designed. Right? So you could say it's a safety factor. You're allowed to go at 70 mile an hour, you're allowed to go at 75, but if you go over 100, we're not, you might go through the barrier. Okay? So you can think of it like that if you wanted to, because the material of the barrier may not withstand you going 100 mile an hour. Obviously, if you look on that F1 the other night, is that F1 yesterday? Did you see F1 crash last night? Paying out. Obviously, there's a lot of factors because there's the angle and there's, what's behind you, if it's a lorry or not. No, they'll stop you going, but if you go 100 mile an hour, they will do something. If they stop you, I've been stopped at 80 and they've gone, on, calm down a bit. But 100, they might tend to give you some points or ban you. Right? Don't go over the speed limit. Don't go over the speed limit. Right? Now, obviously, something with a safety factor of 10. Stop doing that. It keeps trying to share my screen. Safety factor, something with a safety factor of 10, right, is safer than something with a safety factor of 3. Okay? So, Donald Trump's car may have a safety factor. Why would Donald Trump's big limousine thing need to have a safety factor of 10 compared to Lewis James's car by year? Lewis James's safety factor of his car is 3. Why would Donald Trump need to have a safety factor of 10? Correct. Right? Bulletproof. Right? Lewis James made sofas and planes. Look, you haven't got airlines, right? I tell you, if you two have an airline, then I'm the first one to fly in it for free, right? Because I put the idea in your head. Donald Trump's car, safety factor of 10, perhaps, bulletproof, metal sheets on the floor. Lewis James's car's only got 3. Which one is going to be heaviest and more expensive? Which one's going to be heaviest? Yes. This one's going to be more expensive than this one because you've got more stuff. That's called over-engineered. Obviously, Trump needs it, but you wouldn't have a car safety factor of 10 in normal life because it's over-engineered. It's going to be too heavy and it's going to cost you too much. So big safety factors, although very, very, very safe, can be a bit of overkill. It's another good word, overkill. Safety factor. No, well, he's still the president. Not for long though. Okay? That's why the Victorians, if you look at Victorian stuff, Victorians, the Victorians, right? If you look at their bridges, okay, train stations. Think of the one that Brunel built, right? They over-engineered them because they didn't understand the science, right? Over-engineered. Just make them big. Make them big because they got all the money. They got a lot of money. They don't really give a monkeys about health and safety. Make them big. All right. Like, but the Brunel Bridge. If you look at the Brunel Bridge in Bristol, all right. Cost is not right a consideration. So the bigger it is, stop typing, you should listen to me, not typing thing. Right, so Victorians, big bridges, right, because they didn't understand the science, so they thought, right, we don't understand it, we'll just make things bigger. Right, just make things bigger. Now, to work it out, can anybody, right, when we did materials, what does this mean? Daniel Greenshields? What does that mean? What does that mean? I'll give you a clue. This graph that we did from imitate. What does it mean? And where is it on that graph? Right, so the ultimate tensile strength or the ultimate compressive strength, if you remember, it's the top of this graph. Right, and that is maximum. That's the maximum it can take before snap. All right, if you get to that point, it's going to break. That's what we'll assume, right? So if you get to the UTS, that's where it's going to break. That's where it's going to break. You don't want to go anywhere near that, do you? You don't want to go anywhere near that. If you go near this point, it might break, right? You don't want to go anywhere near that. You want to be down here somewhere. This is where Lewis James's aircraft is, down here. Safe, lovely, right? Everybody fly in. Daniel Greenshields is here. All right. So, what page are we on? 12, page 13, unlucky for some. Unlucky for Daniel Greenshields customers, anyway. So, to calculate the safety factor, to calculate this, oh no, I don't want that. To calculate the safety factor, or factor of safety, same thing. You do this. The ultimate, UTS, right? Which is this number here, whatever it is, divided by the working stress. Working stress. WS. Why is it WS? Good question. Working stress. Now all that is the stress that we're working at. Right? 70 miles an hour. Right? Or whatever we've worked out here. So whatever number you've worked out here, for example, like this stress here could be our working stress. It's the stress that we're working at. Now hopefully that stress is nowhere near the breaking point. Right, so it's the ultimate, what this is going to break at. So the ultimate, the UTS, right, is a material property that we know is going to break at that point. If you get anywhere near the UTS, it's going to break. And the working stress is stress recommended. They recommend, right? They recommend you go at 70 miles an hour. Because if you crash into a barrier, the stress that you induce shouldn't break the barriers, right? For example, if I've got a material, right? So this material is going to break at, let's say, 500 megapascals, right? That's the UTS of this material, whatever the material is. It's going to break at 500 megapascals. If you go anywhere near 500 megapascals, it's going to break. You don't want to go anywhere near it. It's the top of the curve. Stay away from it. All right, it's going to break at 500 megapascals. If we say, right, our working stress is 250. All right, so we've designed this plane. We've said don't go any more than 250. You can go below it, but don't go above it. Because if you go above it, we can't guarantee it, right? So we've designed it with a safety factor in mind. Can anybody tell me what the safety factor in operation of this thing would be, whatever this is? Before we do some sums. Bearing in mind, it's the ultimate divided by the working stress. Anybody? Well done, Daniel Greenshields. Because we know the safety factor, or the factor of safety, equals the ultimate over the working stress. So we've said don't go anywhere near 500. Because at 500, we're going to die, right? So the ultimate is 500. Now they're both in megapascal, so you haven't got to put mega in because they'll cancel out. So put it if you want to. That's the stress it's going to break up. We've said Daniel Greenshields has designed his plane, don't go any more than 250 times 10 to the 6. Right? That's what we're working at. So the safety factor is going to be 2. Because 500 divided by 250 is 2. That's the safety factor. It's twice as strong, perhaps, as it needs to be. Now, say if Lewis James said, I want my aircraft to be safer than that. Right, we'd have to fly a bit lower. We have to fly a bit lower, you know, don't rev the engine too much. I only want you to work at 100 stress. What's Lewis's James safety factor? It's going to be 5. Now the plane may be stronger because you've designed it to be stronger, so it's safer, or you just going slower, right? Or not flying as far, but okay. Safety factor of 5 is safer. Most planes have a factor of safety of about 1.6. You'd be surprised. Because the bigger you make something, the more expensive it is. The bridge, the 7 bridge hasn't got much. There's only about 1, so it's between 1.6 and 2.5. They're not massive safety factors. That's the formula. There. That's the formula. Obviously, you've got to keep an eye out now for Daniel Greenshields. That could be your target now, boys. Get your own airline. Don't you remember in 2020 when we were talking about factors of safety? Man Morgan, we did that. Oh yeah, look at me now, Daniel Greenshields. I've got 65 airlines. And Lewis will have 72. Not that we'll have any pilots by then. Right, we'll do one more, and I have a bit of a break. I'm going to carry on with science today because I want to finish this topic. So there'll be no materials today. I want to finish this off because I want to give you an assignment perhaps next week. So we'll have a bit of a break though, right, in a bit. 14, let's do something else. Let's do this now, right? Let's do a question. We're not having a break yet. 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 We'll do another question. Do another question. Now, let's, for example, do let's do one like this. Let's say we've got a, I don't know, when should, we're not going yet. Another question. We'll do this one and then we'll have a bit, because my mouth is going to be dry now because I'm talking. Shut up, Alex. What have you got, Alex, to eat? Let's just say we've got this metal bar or something, right? Here's my metal bar, right? Metal bar. Diameter is 10 millimeters. It's got a, I don't know, force coming this way. 17 kilonewtons. 17 kilonewtons. 17 kilonewtons. If you make them nice mince pies, Lewis, you get distinction. Length, it starts off, length is 600. Right. The force then pulls it, right? So it stretches to, I don't know, 637. So this force pulls this little bar, right? And the final length is that much, right? So we need to find stress. We'll find the stress, right? And we'll find the strain. Okay. Let's pretend this bit of metal, right? The UTS of this bit of metal is, right? Let's give you 250. Let's see if we can make it break, right? So whatever this bit of metal is, it's going to break at 250. So we need to work out now factor of safety as well. Factor of safety. So stress, strain, and factor of safety, right? Hopefully, whatever we get for the stress is lower than the 250, right? Because if it's not, we're in the stock. So stress, to begin with, easy. Force over area. So stress is force over area. We know the force. The area is going to be pi d squared over 4. Pi d squared over 4. Right. Right, there's pi. D is 10 mil. Don't forget, divided by 1,000. Square it. Divided by 4. That's the area. No news there. It's the same as before. 10 divided by 1,000 to get into meters. We'll square that, times it by pi, and divide it by 4. Can somebody do it so I know we're correct? 78 something. So make sure we've got 78.54, say something. Times 10 to the minus 6. That's the area. Type a dot if you agree with me. And the force is 17,000. So it's 17 times 10 to the 3. Oh, hello, Connor Richards. Hello, Connor Richards. You just turned up. You just turned up, Connor. Oh, Connor Richards. You've just turned up, Connor. Connor. And Ty's just turned up. What's going on? Where have you been? 2:30. Forgot. You forgot. Forgot. Yeah. Where were you really? Funny that both of you came in together. I bet you've been playing FIFA together, haven't you? This is recording, lads, right? And I have to mark it I was late, though. 14:37. I have to mark it I was late. Doesn't affect your attendance. Internet were down, actually. So, because it's a legal document, so Connor and Ty, I'm glad you're here. We're about to have a break, actually. 14:37. Doesn't affect you if you hear me, right? But so somebody give me that stress, please. 17 to the power 3. Divide that by 78.54. 0.54 to the minus 6. Should give you a number. Not yet. Well, shut up. In a nice way. What's the answer? 216 mega. Well done, Joe. Don't forget the mega, Joe, right? But you're correct, right? Pascal, yeah. That's how much stress we've got on this thing. Huh? Now, before we do strain, is this thing going to be safe? Bearing in mind it's going to break at 250. So the safety factor, right? So our stress is below 250, right? So it's just about safe in it. So when we get to that, it's looking all right. So we've done the stress, we need to do the strain. So 15, 16, we know strain. I keep touching on my iPad. Strain is change in length over original length. So what is the change in length? Well, I don't know, but I do know because we've got 600.37. So 600, yeah, really, 600.37, it stretches to that much. It starts off at 600, so do that. You shouldn't really need to do it, really. But my change in length is 0.37 because it stretches to 600.37, starts off at 600. So the change in length is 0.37 of a millimeter. Type I, if you've seen that and understood it. So change in length equals 0.37 of a millimeter. It starts off, the original length starts off at 600 mil. 600 mil. All right. We've got to find the strain. So as long as they're both in the same units, everyone's a winner. They both are in the same unit, so we'll keep them in millimeters, save changing them about a bit. Get the same answer. 0.37 divided by 600. Right. Strain is 0.37 divided by 600. They're both in millimeters, so everyone's a winner there. Look, you can convert them both into meters if you want to. 0.37 divided by 600 gives you a small number. What's it give us, Lucas Banks? You're the last one to type. What's it give us? 0.37 divided by 600. This is the strain, no units. As long as they're both in the same units, you should get the same answer. Lucas Banks, Lucas, 616.67 times 10 to the minus 6. Right. No units, it's just a ratio. Right. That's strain done. We found the change in length. Yeah, of course you will. Yes, London Lucas. There's people do type quick. The change in length is 0.37. That's why we got it, because we have that and that. The last one is factor safety. Factor safety. So safety factor or factor of safety makes a difference. Safety factor, if you remember, is the ultimate, right, tensile, because we're pulling apart, divided by the working stress. Now, the ultimate is here, 250 mega. That's the ultimate. It's going to break at 250. So 250 times 10 to the 6. It's going to break at that. The working stress is what we've just worked out. The working stress is what we've just worked out, which is 216 mega. So put that in there. You haven't got to put the mega because it cancels out, but just in case, it's not always mega, right? 250, it's going to break at 250 because we've got it here, there. And the working stress is 216 because we worked it out. Here's your chance, Lucas. What's the safety factor? Before anybody else says it. Safety factor. If it's above 1, everything's good. If it's below 1, we've just crashed into the sea at Neyland. 250 divided by 216. Is that what you're going to say, Lucas? Were you going to say the same answer, Lucas? 1.15, 1.157. Right? It's just about, isn't it? It's over 1. Anything over 1 is okay. So it's just about. Just about. I wouldn't go any more than 216. Right? So it's fair. It's just about safe. Probably just about perfect because you haven't got any wasted engineering materials. It's just about safe. As long as you stick to 216. Does everybody understand factor of safety? Type a dot if you understand factor of safety. Answer this poll if you're still here. Right. Are you still here? Are you still here? Yes or no? Are you still here? Yes or no? Let's see. Because you probably need to calculate strain. We could work out Young's modulus if you wanted to, but I just wanted to do safety factor first. You'll always have to, these questions, you'll always do strain, stress, Young's modulus, things like that. Right. We're all still here.